Hi, hello guys. Look, this is the continuation of symmetrical fault uh, again, and we are getting now to a more advanced and practical problems, but they are also done at the university. And normally these problems are taken from the principle of power system protection. That's the name of the book. I can't remember it's written by who, but normally they are student problems. Let's get to a more advanced ones. They are still the same. It's just that more things are added now. Say maybe uh, the grid start to have maybe 3, 4 or more generators or alternators, and then the lines as well, and then we start putting more reactors into the system. The plant capacity of a 3-phase generating station consists of 10,000 kVA generators of reactors 12% each 5,000 kVA generators of reactors 18%. The generators are connected to the station bus from which the load is taken through 5,000 kVA step up transformer, each having a reactance of 5%, taken through 5. I think it is taken through 3. I think I forgot 3 there. Yes, it should be 3. I remember. From which the load is taken through 3 5,000 kVA step up transformers, each having a reactance of 5%. Yeah, it should be 3. Determine the maximum fault MVA which the circuit breakers on condition number 1, low voltage side, 2, high voltage side may have to deal with. The short circuit NVA on the low voltage side and high voltage side, to which the circuit breakers have to deal with it. Now, the plant capacity of it. You still remember what a plant capacity is? I think I think a plant capacity was what? It's actually an indication of reserve of the generating station. You remember the plant capacity factor, where it was the ratio of the energy produced over the maximum possible energy that could have been produced. So this plant capacity, it is actually the maximum possible energy which the station produced. And if you cross remember, man, you know those things, that the difference between the load factor and plant capacity factor is an indication of the reserve capacity. We remember the plant or the generating station must have a reserve so that it should be able to deal with the increased demand that will be needed in future. We know those things. From university. Let me, if I may put it that way. Now, the plant capacity of a 3-phase generating station consists of 10,000 kVA generators of reactors 12% each and 5,000. There's three generators. This and 5 is something like this. And remember, always the generators provide supply power to the bus. to the bus bars. These are generators. We can say generator A, which consists of what? It consists of 10,000 kVA, and it has its internal percentage reactance of 12. This one as well, this one, and it has 12%. And then you are told that and a 5,000 kVA generator, and this one has its internal reactance of 18%. Now, from which the load from this bus is taken through 5,000 kVA. Okay, van Strijer, something like this. (5,000 kVA step up transformers. Something like this. And then it's, that transformer is what? It's 5,000. Each one is 5,000. 5,000 kVA. 5,000 kVA. 5,000 kVA. And then these transformers each have got, each one has 5% reactance. 5% reactance. And then what? Determine the maximum. Okay, this thing it has to go through something like this. Determine the maximum fault MVA. Okay, MVA. Let me write it properly. Short circuit MVA is equals to question mark. Determine the maximum fault NVA which the circuit breakers on the low voltage. Remember, this transformer is a step up transformer, meaning this side is the low voltage side, this side, this transformer. We did transformers, you know what is a step up transformer is. That one, it is meant for a high voltage transmission. Then it stepped up the voltage. Why? It's going far. Why? To cater for voltage drops along the lines and stuff. And so that, remember, at the supply end, we call it what? The receiving end voltage. We know. We'll deal with transformers very soon. Okay, right. All right, something like that. For which the circuit breakers on the low voltage side should be able to manage. The circuit breaker should be able to manage the short circuit NVA on the low voltage side. You also, for condition 2, you have to calculate it on this side. Actually, you are determining what size of circuit breakers you should put on the low voltage side in order to counteract this short circuit MVA, and also on the high voltage side. And then yesterday we know what is now a symmetrical fault. Is those faults that gives rise to the current in a three-phase system of which they are 120 degrees apart. We know that. And then we know as well that it happens only when this, very, very important, it happens when these three phases are brought together under short condition. If they are brought together, very, very important, and you will see as well, only one phase is considered for the calculations. Why? Because the same conditions prevails on the other two. If the same conditions are the same on the three phases, we consider only one phase because the conditions are the same on the other two conductors. We also mentioned that the impedance yesterday, that the impedance of the system is the only one that opposes or impedes the fault up to its point where it has occurs, that information is very, very important, very, very, very important. We also mentioned that the voltage at the fault is normally 0, but we express it in terms of short circuit kVA, where we multiply the system voltage and the current. But in a 3-phase system, you only put in 3 there to show that it's 3-phase, and then voltage multiplied by current, we know it is kVA, is volt amps. That's where it comes from. Now the fact that I don't have space, guys, like we said yesterday, I normally, you can choose any base. We have to choose a base. Why? We've got different ratings in the power system, so we have to refer the percentage reactance of all the equipment to the same common base. So we choose the most preferable one, and it should be equal to what? It should be equal, in my view, it should be equal to the largest rating. In this case is 10,000. I'm gonna choose 10,000 kVA. I don't have space, that's why I'm forcing there. I choose 10,000. You can choose 5,000. We still gonna get the same answer. Why? Because that common base you are choosing, it has no effect at all to the short circuit current. So you can choose any one. It is an unimportant value actually. So here, meaning here, the percentage reactance of generator A is equal to what? Is equal to 10,000 divided by 10,000 multiplied by 12. We've got 12%. This is the same as well. You can make calculations, but the conditions are the same. Percentage reactance of generator B is also equal to 12. Here we've got 5. You have to do calculations. Percentage reactance of generator C is equal to what? 10,000, a chosen one, over 5,000, multiply by 18%, and it is equal to what? 10,000 divided by 5,000 is 2. 2 times 18 is 36. 36%. Very, very important. Here, we only gonna choose one phase. Why? The conditions are the same in all phases. So for that reason, it's gonna be percentage reactance of the transformer is equals to what? Is equals to 10,000, sorry, is equals to hey guys, where can I, okay, it's fine here. It's equals to 10,000 divided by 5,000 multiplied by 5%, and it's equals to what? 10,000 divided by 5,000 is 2. 2 multiplied by 5 is 10%. Is 10%. Is 10%. Now, let's do this. Will I be able to see what's going on? Let's continue. Let me continue. We will see here, guys. Now, let's say, for instance, this is my neutral, for instance. My neutral. And then we're going to have this one. This one. This one. This one. And then, of course, this is your bus bar there. And then you have chosen only one line. You can choose this one. You can choose any line. And then this one, it is 5%. 10%. Sorry. It's 10%. This one is equal to what? This one is 12%. This one is 12%. This one is what? It's 36%. It's 36%. All right, Van Strayer. Alright, van Strayer. Alright, van Strayer. Hey guys, we are done here. I'm gonna delete this. I'm gonna delete this. I'm gonna delete this. I don't think we're gonna need this one. I don't think I'm gonna need this one. Actually, what we drew here, like we said yesterday, you have to have a single line diagram. This was the single line diagram derived from this information. Here, we have drawn the reactance diagram corresponding to the single diagram there, as you were aware. And then this is the reactance diagram. And then let's calculate. Now we are trying to calculate the total reactance of the system. Let's do everything together and then we analyze what the question wants. Now here, first let us start with the percentage reactance of the parallel combination here. And it is equal to what? Very, very important. From short schools, primary one, you used to say the resistance of the parallel branch is 1 over 12, this one, plus 1 over 12, this one, plus 1 over 36, this one. If you say percentage reactance is equal to 12 multiplied by 12 over 12 plus 12. This formula is very important and good, but it only limits you to 2 reactances. After that, you have to calculate another parallel combination. So I've used this formula to make sure I take all the parallel combination together to calculate the total parallel combination. But this one is nice in this way. It takes you strictly to mathematics basics. Mathematics basics, the language of engineering, mathematics. You have to find the lowest common multiple, which is what? It's 36. What is the lowest common multiple? It is a number that all the denominators can go into it without having a remainder. That's the lowest common multiple. This one into this one 3 times. 3 multiplied by this one is 3. Plus, same story here. This one into this one once. 1 multiplied by 1 is that. And you get what? You got 7 over 36. Therefore, remember this actually it should be 1 over percentage x parallel. This percentage x parallel reactance. But now you have to swap it such that this one should also go on top. 1 over x parallel is 7 over 36. Therefore, percentage x parallel is equal to 7 over 36, which is equal to what? It is equal to 7 divided by 36. 7. What's going on here? Oh, it should be 7 here. Sorry. It should be plus 1. It should be 7 divided by 36. 0, comma. Is that okay? No, it can't be that. This into that, it's 0. Is it 7? 3 plus 3. This into this 3 times. 3, 12, 24, 36. And then 3 times 1 is 3 plus 12. This one once 1, yeah. This is equal to 7 over 36. 7. Oh, I have to juxtapose it. Sorry, I really apologize. This should now be 36 divided by 7. I swapped it around. It should be 36 divided by 7. I really apologize, guys. I was 143%. This is the total reactance of the parallel branch. Now we've got this. This is now limited to, this is our neutral point. It is now this, which is 5,143, and then in series with this one, and this one is equal to 10%. Therefore the total reactance of the whole system is equal to 10 plus 5 is 15,143%. All right, Van Strayer. Now I can delete this. This is also done. I can only be left with that one. Now let's see, guys. We are coming to the conclusion of this. They say we've got generators, we've got transformers, we've got lines. So here it was what? I can't remember. Or they say on the low voltage side, this is transformers. Low voltage side, there on the low voltage side. High voltage side, there. That's the high voltage side. Is that correct? Yes, it is correct. So here we've got what? We've got short circuit MVA. On the low, short circuit MVA is equal to the base of 7.5 multiplied by not 7.5, 10 divided by percentage. Here on the for the low voltage side, up to that point is 5. Yes, percentage X, and then this one is 10,000 multiplied by 100 over this one. There is that one is 5 5,143, and it is equal to what? This is for the low voltage side. The impedance of the system can only oppose the fault up to that point. And there at that point it is 5, the reactance is 5,143, and it is 100 divided by 5,143 multiplied by okay. They say we've got how much here? We've got 10,000 watt. Let's check. Where is 10,000? Okay, we have chosen 10,000 kVA. 10,000 kVA. Let's divide it by 1,000 to make it MVA. Okay, Van Strayer. It's 10,000 divided by 1,000 is so much, multiply by open brackets 100 divided by 5,143 closing brackets. Answer is 194,444 MVA. Right. Now they say this is for the low voltage side, condition number 1. But now what about the high voltage side? The high voltage side, this impedance is for what? Yeah, this impedance is for transformers. We don't have the ones for the line, isn't it? We've got this, we've got this. Yes, this one is on the high voltage side, so we're gonna use the total impedance there. Yes, so it's short circuit MVA is equal to this 10 multiplied by Y10 is 10,000 divided by 1,000 is 10 multiplied by 100 divided by how much? 15,143, and it's equals to what? this divide by 15,143 multiply by 10. Yes, 66,04 MVA on the high voltage side. What does this statement says? It means the circuit breakers of the higher ratings, they're gonna be on the low voltage side, and then the ones of the ones for lower ratings, they're gonna be on the high voltage side. Why? Because on the high voltage side, you can see here, this short circuit MVA is smaller than the one that appears on the low voltage side. Guys, please subscribe, share this video, like it, and don't forget, on the 31st of October and the 1st of November, we will be in Rustenburg. You're gonna get people who are used to this on practice: engineers, engineering managers, supervisors, chief electricians. Everyone will be there. Just be there, but come prepared. Come with problems that you think maybe they are of pitfalls to you. They say on that seminar is winders, but it's gonna be a combination of everything that is related to the winder: cable, transformer, protection devices, winding, and so on. We've got a very, very interesting people there. I will also be there watching and see what's going on. But thank you very much, guys, man. Thanks for giving me an attention. I love you all. Mwah. Shapra.